Welcome back, everybody. We are to part 2 of chapter 8, and we are finally going to do a full-on hypothesis test. The second part is specifically about proportions. And if you found the previous video a little all over the map, that's because it sort of was. And this video is to help us kind of tie it all together to make it all one thing. So we're going to conduct formal hypothesis tests of a claim about a population proportion, P. The requirements, the sample observations are a simple random sample. Conditions for the binomial distribution are satisfied. All the examples I'm doing will. And NP and Q has to be bigger than or equal to 5. Again, all the examples we're doing, they will. So let's just jump into it and walk through the process and come to a conclusion. Example 6. Nexium is a drug that can be used to reduce acid produced by the body and heal damage to the esophagus due to acid reflux. The manufacturer of Nexium claims that more than 94% of patients taking Nexium are healed within 8 weeks. In clinical trials, 213 of 224 patients suffering from acid reflux were healed after 8 weeks. Test the manufacturer's claim at the 0.01 significance level. Where do we even start? We start with the null hypothesis. The null hypothesis is that the proportion is 0.94. And the claim claims more than. So that means P is bigger than 0.94. This is going to mean that we're going to have a right tail. And to be clear, this is the claim. All right, so these are Z values here, and we are using an alpha of 0.01, and because it's greater than, it's going to be a right tail. So this area here is 0.01. And what we're going to do is we're going to find the critical value based on that. And if you remember, with inverse norm, it has to be area to the left. So this is going to be 1 minus 0.01. All right, there's our critical value. And we have 2.326. The red is the critical region. And whether our test statistic is there going to be in there or not in there, that's going to be our next piece here. Next up, we're going to run a 1 proportion Z-test. Now, most of these tests and even confidence intervals and so on are going to be under stat, under tests. And you can see this is a 1 proportion Z-test. P is 0.94. X is going to be the numerator. That's here. That's the 213. N is just regular old N. That's 224. And in this case, it's greater than. And what we're going to get is the test statistic. And we're going to use that test statistic to compare to our critical region. So here we go. All right, our test statistic is going to be Z is about, what do we have? 0.68, which is about right there. And our p-value is right here, 0.2462. Now there's 2 ways to look at this. I can talk about my test statistic is not in the critical region, or I could say that my p-value is way bigger than my alpha. Both bring us to this exact same conclusion. Because we are not in the critical zone, or because the p-value is bigger than the alpha, we fail to reject the null hypothesis. This means that there is not sufficient evidence. Evidence to support the claim that mixing has a higher proportion than 94%. That's the whole thing. So again, the null hypothesis, we're assuming that's true going in. That's just sort of the assumption. Someone's making a claim that it's not true, that there's something else. Therefore, the burden of proof is now on the claim. Now, I want to make this similar to a court of law. You'll notice that the verdict is always guilty or not guilty. It never says innocent. And the reason for that is because notice we're not accepting the null hypothesis. We simply are failing to reject it. So I'll let that kind of simmer while we move on to the next example. Example 7. In a poll, 38% of adults with children under the age of 18 reported that their family ate dinner together 7 nights a week. In a recent poll, 403 out of 1,122 adults with children under the age of 18 reported that their family ate together 7 nights a week. Has the proportion of families with children under the age of 18 who eat together 7 nights a week decreased? We're going to use our alpha of 0.05. All right, so here we go. Our null hypothesis is that it's 0.38. The alternative hypothesis is that it is decreased. Once again, the claim is on the alternative hypothesis. All right, so let's build our critical region. It's less than, so it's going to be a left tail. Our alpha is 0.05. So we're here. All right, let's find our critical value. Inverse norm, area to the left is 0.05. Negative 1.64, we'll say. So we now have our critical region, and we need to find our test statistic. Test statistic. So we are going to run, once again, one portion z-test. Stat tests one test 0.38, and in this case our x is 403, n is 1122. N is always larger, by the way. This one is less than. Let's see what we get. Z is, so our test statistic Z is negative 1.4368, which is about right there. I'm over exaggerating that just a little bit. And our p-value is here, p-value 0.075. So p-value which is definitely bigger than our alpha. So what is our conclusion? Once again, we are going to fail to reject the null hypothesis. So there is not sufficient evidence to support the claim that, I'm not going to write it all out, but the children under the age of 18 eating 7 days a week and so on. You can see it's not so bad. You, of course, on a test are going to have to write all that out. But I don't want you to watch me on a video doing a bunch of writing. All right, example 8. In 1994, 52% of parents of children in high school felt it was a serious problem that high school students were not being taught enough math and science. A recent survey found that 256 out of 800 parents of children in high school felt that it was a serious problem. Do parents feel differently today than they did in 1994? So our null hypothesis is that P is 0.52. Our null hypothesis is that it's now different. And not equal to, remember, that gives us a two-tail test. So we have, I like drawing this every time. I think it gives a very nice visual, not just for students, but it'd be good if you drew it as well, because it'll really help you visually understand what's going on. So our alpha is 0.05. So we're going to split that up into a couple pieces. Cut it in half, right? Half of 0.05. And just to be clear, our alpha is 0.05. Where is it? 0.05. 0.05 divided by 2. That's where I'm getting the 0.025 from. Let's find our critical values. That's going to be inverse norm, 0.025. And the nice thing is, once we get the negative one, which we're going to get right now, that is also going to be the positive one. So negative 1.96. That means this one is 1.96. Now, I will demonstrate to you that that's true. Inverse norm, 1 minus 0.025. And you can see it's the positive version of that. Next up is the test statistic. All right. So we are stat tests, one prop z test, one proportion z test. We have 0.52. Numerator in this case is 256, 256 of 800. This is a not equal to problem. Let's see what we get. Our z is negative 11. Holy cow. Now, if you remember, a z are the number of standard deviations away from the mean being here. So we are negative 11.32. Wow. And the p-value, and by the way, negative 11.32, that's obviously not even on this graph. The p-value looks a little funky. Looks like it's more than 1, but in actuality, it's times 10 to the negative 29th power. That means I would move that decimal to the left and have 28 zeros, and then the 1 and the 0 and the 3, the 9, 6, 1. So basically, we say that that is about 0, which 0 is definitely less than the alpha. This is the 0.05. So for this one, we're going to reject the null hypothesis. Meaning there's more validity to this here, that it's not 52% anymore. So there is sufficient evidence to support the claim that that the v-lengths have changed. Meaning attitudes, whether parents think it's a serious problem that they're not getting enough math and science. So there's a taste of our brand new hypothesis testing. I once had a student that said, hey, can I actually use this in real life? And the answer is yes, you can. Just make sure when you gather your data that you're gathering it without bias.